Hi, this is Math Kimchi, and today we will be learning about sequences. Now, sequence is just another name for a list, and just like lists, in sequences order matters, and there can be multiple terms with the same values. And sequences are like functions, is one way you can describe them, and they are notated like A1, A2, A3, and then AN, and it can keep on going forever or be finite. And when I say that sequences are like functions, I mean that this would be like the input of the function, and the domain of sequences are positive integers, and it can go up to infinity, or if it's a finite sequence, then there will be a custom stop point. And that just means that in n has to be a positive integer. And also, usually it starts with A1 instead of A0, which makes things kind of confusing, especially if you're implementing things with sequences into programming. And two very common types of infinite sequences are arithmetic sequences and geometric sequences. So first, let's look at arithmetic sequences. Each arithmetic sequence has a common difference, and every next term is the previous term plus the common difference. And common difference is also notated as D a lot of times. And for example, 2, 5, 8, 11, 14, 17, 20 would be a arithmetic sequence because the common difference is 3, and when we go from 2 to 5, we add 3 again, add 3 again, add 3 again, and you get the point. And also, the common difference can be negative, so we add -2, -2, -2, -2, or you can think of it as subtracting 2. And the common difference, if it doesn't say explicitly, you can just subtract one of the terms minus the previous one. So for example, 20 minus 17 will be equal to 3, and -6 minus -4 is equal to -2. And the common difference for this sequence is -2, and for this it's 3. So it works. And it works no matter where you do it. So you can start from 5 minus 2, that's also 3, and 2 minus 4, that's also -2. And there are two basic equations for arithmetic and geometric sequences. And the first one is the recursive equation, and if you saw my programming videos, you would know that in a recursive function or equation, it basically calls itself. So in the function a of n, or the nth term of a, it equals to a of n minus 1 plus d. So it's basically calling itself in here. And make sure that d is an actual number, is a constant when you are giving it. And you also have to make sure to give a base case, and the base case is going to be a1 equals to, for example, 2 or something like that. So let's create a recursive equation for the first sequence. It would be, so first we have to find d, and d is just any of these terms minus the previous ones. So 14 minus 11 is 3. And we also have to find a1, which is just the very first term, and that's 2. And now we can plug in d to the an equals an minus 1 plus d. Or I guess we can find the d's and a1s for this one. So this would be d equals -2, and then it would be a1 equals 4. And we can get d equals -2 by doing like -4 minus -2 equals -2. And now we can plug in d equals 3 or d equals -2 into the recursive equation. And we have an equals an minus 1 plus 3. And we also have another equation, a1 equals 2. And if we didn't have a1 equals 2, the problem would be that we wouldn't know. If I wanted to find, for example, a5, then it would be a4 plus 3. And to find a4, it would be a4 or a3 plus 3. And we keep on doing that until we have a1 plus 3. And usually we would know that a2 is a1 plus 3, and we know a1, so it's 2 plus 3. But if we didn't have this part, then we'd just keep on going down, and that wouldn't even work for sequences, because sequences can only, there can only be positive integers for n. And yeah, long story short, we need to state the base case so we know where to kind of start. And also for this sequence, let's just plug it in, and we have an equals an minus 1 minus 2, so that's d, and a1 is equal to 4. Now let's talk about geometric sequences. Geometric sequences are actually pretty similar to arithmetic sequences, but the difference is that instead of adding, you multiply. And so instead of having a common difference, we have common ratios, and you get the next term by multiplying the previous term by the common ratio, also known as r. And so, for example, in 8, 12, 18, 27, r is 3 over 2, and in 4, 2, 1, 1/2, and so on, r is 1/2. And you see that 8 times 3 over 2 is equal to 12, 12 times 3 over 2 is equal to 18, and so on. 4 times 1/2 is 2, 2 times 1/2 is 2, and you see the point. And the recursive equation for a geometric sequence is an equals an minus 1 times r. So we see that it's just times r instead of plus d. And yeah, now let's find a1 for both of these so that we can have the base case. And now our recursive equation is going to be an equals 3/2 times an minus 1. And I just moved r to the front for formatting purposes. And we also need to have the base case, which is a equals 8, for the same reason as before. And we can do the same thing for the next sequence. And actually, wait. Sorry about that. This should not be 3 over 2 times a. It should be, let's see. Yeah, this should be 1/2 and 1/2, and a1 should be 4. So this is the recursive equation for this geometric sequence. And for example, if you wanted to find a4, which is 1/2, we would have 1/2 of a3, and a3 is 1/2 of a2. a2 is 1/2 of a1. Oh, and we know a1 is equal to 4, so we have a2 equals 4 over 2, which is 2. So a2 equals 2, and a3 is equal to 2 over 2, which is just 1, and a4 equals 1 over 2, which is 1/2, and a5 is equal to a4 over 2, and a4 is 1/2, so a5 equals to 1/2 over 1/2, or yeah, 1/2 over 2, which is equal to 1/4, or 1 over 4. And the general formulas instead of recursive formulas are an equals a1 plus d times n minus 1 for arithmetic sequences, and for geometric sequences it is an equals a1 times r to the n minus 1. And we kind of see why this makes sense, because first of all, there's a minus 1 because if this was a0 instead of a1, there would be no minus 1, but since we start at number 1, and for a1 we add nothing, and so when n is equal to 1, this should be 0, and we do that by just subtracting 1. And it's kind of similar to a linear equation, but and this is kind of like the intercept, but since it starts at 1 instead of the y-intercept being when x equals 0, this is when x, aka n in our case, when n equals 1, and that's why we're subtracting by 1. And it's also the same for this, but this is more like a exponential equation. And yeah, this would be like the slope, and this would just be x, or x minus 1, if it was a linear equation. And it's similar to geometric for geometric, and for this equation it's similar to exponential. And now that we know what we have to know about the arithmetic sequences and geometric sequences, let's try three problems. And I recommend for you to try solving these problems before you keep on watching. So if you're gonna do that, then pause the video. But now I'm going to explain the first problem. So problem 1, we have to find the general equation, recursive equations, common difference, or ratio. It's going to be common difference for this one. A1 and the 10th term for the arithmetic sequence, where A2 equals 13 and A4 equals 25. And so for things like this, we're usually going to use the general equation, which is an equals a1 plus d times n minus 1. And for basically everything, the general equation is going to be more useful than the recursive equation. And since we know the general equation, let's just plug A2 equals 13 into the general equation, and also A4 equals 25. And when we do that, we have A2 equals A1 plus D times 2 minus 1, and something similar but instead of 2, it's a 4. And for A2, we can plug in 13, and for A4, we can plug in 25. And we can also do the subtraction in here. And now we can put this equation under this equation and do solving by elimination. And if we subtract this from this, we have 12 equals 2d, and that gives us that d is equal to 6. And so we can plug d into both of these equations, and solving both of these equations should lead to a1 being the same value if we did this correctly. So we multiply everything, and then we just subtract, and we get that a1 equals 7 both times. So we found out the a1 and also the common difference from just plugging things into the general equation. And now that we have this, we can plug this into the general equation. So a1 is 7 and d is 6. And if we wanted to, we can also distribute the 6. And so we have 7 plus 6n minus 6, and that's just 6n plus 1. And we can do something similar for the recursive equation where we just plug everything in. But we're not going to plug this in, because then we would just say 7 equals 7, and that's not really helpful. And also, to find the 10th term, we just plug in n to the general equation. And we could do it with a recursive equation, but it wouldn't be fun. It would be very repetitive. And yeah, if we just plug in n as 10, we get 8, 10 equals 6 times 10 plus 1, which is just 61. So now we have everything for problem 1. And for problem 2, we do something similar, but for geometric sequences. And in this one, it gives us the A1 directly, so we don't really have to search for that. And there are 2 places we can find the common ratio, which is 45 over 27 or 75 over 45, and both would work. So we can, and both would be the same thing, assuming that this is a geometric sequence. And so we can just say that r is equal to both of them, and they both say it's 5 over 3. And now we can find the general equation, just plug everything in. And oh yeah, we can also like distribute out the 5/3. And so if we ignore this part, 5/3 to the power of n minus 1 is the same thing as saying 5/3 to the power of n times 5/3 to the power of -1. And 5/3 to the power of -1 is the same thing as saying 3/5, because when it's a negative, it's a reciprocal, or you just flip the fraction upside down. And now we can just multiply 27 by 3/5, and we have a simplified version of the original general equation. And for the recursive equation, we just have to plug everything in again, but not the first A1. And now we have both the recursive and general equations. And to find the A10, we can just plug in n into the general equation. And for this one, you're gonna need a calculator, and it says that the answer is this big number, so it's 1,953,125 over 729. So, or you can say it in a decimal form. It doesn't really matter, since that's not the important part. But now we have everything we need for problem 2. Now for problem 3, this one is the hardest one in my opinion, and we have to fill in the blank for the geometric sequence 81, and then blank, 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 and A5 is equal to 625. So this is kind of similar to the very first problem we did, where we didn't know all of the things in between. So we can just plug in everything into the general formula, or the general equation. And we can plug in A1 equals 81, and also A5 equals 625. So if we just plug in, oh yeah, we don't really need to plug in the first one, because it's not gonna help us, but we can still use it. And instead of having A1, we can just do 81. And for R, we don't know that, but n is going to be equal to 5. And now we have A5, or 625, is equal to 81 times R to 5 minus 1. And we can just replace A5 as A5 with 625, and 5 minus 1 just becomes 4. And we can divide out, and we have that 625 is equal to 81, or 625 over 81 is equal to R to the 4th. And now you may be thinking that we can just take the 4th root of this entire fraction, and that would be R. And you would be right, but we're actually missing 3 more solutions if we do that. And so you have to remember, when you take the square root or the 4th root or any even root of a number, or of two two sides of an equation, we have to remember that oh yeah. Okay, well, before we do that, we can say that r to the fourth is equal to 5 over 3 to the fourth. And we can't just say that r equals 5 over 3. And the reason why is because when we take the square root of something, or of a equation, we have to have a plus minus. Because if we had, for example, x squared equals 1, x could be 1 or negative 1. And when we have x to the fourth equals negative 1, we have x can be 1, negative 1, but we also have x could be the square root of 1, or the square root of negative 1, and also the negative square root of negative 1, also known as just I and negative I. So let's take this step by step and take square roots 2 times. So we can say that this is just the same thing as saying r squared and then is equal to 5/3 squared. And now we can take the square root, and when we do this, we can say plus minus on just this side, and the squares cancel out, and we have r squared equals plus minus 5 over 3 squared. And already we see that there are at least 2 solutions for r. And when we square root this again, we have plus minuses again. So we have plus minus the square root of plus minus 5 over 3 squared. And that's equal to the square root of r squared. And we can get rid of the, or before we do anything, I guess we can have 2 different cases. And so the first case is if this one was positive, and the second case is if this thing was negative. So here it's positive and here it's negative. And when we take the square root of that, we have r can be plus minus 5 over 3, or r can be plus minus 5i over 3. And that's also the same thing as saying r equals 5 over 3, or negative 5 over 3, or 5i over 3, or negative 5i over 3. And the u here is the same thing as a union, and you can just think of it as or. So r can be 5 over 3, or it can be negative 5 over 3, or blah blah blah. And now we can just multiply all these by 81 to over and over again. And to be more organized, let's do it in a chart. And each row is a different possibility for r. So let's just fill that in. And we know that A1 is going to be 81 no matter what, and A5 is going to be 625 no matter what. And now we just have to solve each row. So 81 times 5 over 3 is 135, and so on until we get to 625. And this is the same thing, but instead of multiplying by 5/3, we are multiplying by negative 5/3, so we see that it's just the same thing as this, but then it alternates from plus minus. And here we have the same thing again, but it's 5i over 3 instead of 5/3 or negative 5/3. And finally, we have negative 5i over 3. And yeah, every time we just multiply 81 by negative 5i over 3. And so 81 times negative 5i over 3 is negative 135i, and that times negative 5i over 3 is 225, and so on. And now we solved all of the problems, and we learned about geometric and arithmetic sequences. So that's it for this video, and see you later. Bye.